Assalamualaikum and good day to everyone. Our team from Plus One are going to present on the topic of deadlock. My name is Arif and our team consists of 4 more members. First is Kishan, Afif, Nabila and Nazrin. As an introduction, it is known that system consists of resources and processes, and for every resource R contain W instances. There are 2 types of resources. The first one is logical and the second one is physical. An example of logical resources include database records and semaphores, while few examples of physical resources include printers and disk drivers. A process could utilize a resource by requesting, using, or releasing the resources.
Okay, what is a deadlock? In terms of theory, deadlock is a state when every process in the set of processes is waiting for an event that can be caused only by another process in the set. Okay, now we need to know why the deadlock can happen. The deadlock will occur due to these 4 conditions, which is no preemption, hold and wait, mutual exclusion, and circular wait. For no preemption, a resource can be released only voluntarily by the process holding it after that process has completed its task. For hold and wait, a process holding at least one resource is waiting to acquire additional resources held by other processes. For mutual exclusion, only one process at a time can use a resource. For the last one, circular wait, the waiting processes form a cycle. For example, a resource A waits for resource B to finish up the process, while resource B waits for resource C to finish up the process also, and resource C need to wait for resource A to finish up the process. That's why it's called a cycle and it's a circular wave.
One example of deadlock in real-life situation is updating database. Generally, updating database is not an example of deadlock. However, depending on the situation and circumstance, it could also be a deadlock. In this situation, Michael and Sarah both are trying to access the same table inside the same database. They want to change the value, they want to updating the value of the same table. This situation could be represented as Michael a process, Sarah a process, so there are 2 different processes. Both are trying to access the same resource, which is in this case the same table inside the database. Thus, this situation results in a deadlock.
For this part, I'm going to talk about the resource allocation graph, which is RAG. So, what is RAG? Resource allocation graph is the pictographic representation of the state of a system. In other words, it is the graphical representation of the state in the system in terms of processes and resources. Okay. There are 2 main components of RAG, which are vertices and edges. So, first, let's talk about the vertices. There are 2 types of vertices in RAG, which are process vertices and resource vertices. And resource vertices can be divided into 2 more smaller groups, single instance and multiple instance. Okay. What does process vertices and resource vertices mean? Process vertices is a representation of a process in the system. It is represented by a circle, and inside the circle we mention the name of the process. Okay. For the example, we can see there is a circle with P1 inside, which means this is process 1. This is process P1. Sorry. And the next one is the resource vertices. It represents a resource represented by a rectangle. We use n dots in the rectangle to mention the n amount of instances in the resource. So let's say there are, for the example, there are 4 instances in the resource. So there are 4 dots. If there are 3 instances, so we use 3. Okay. Okay, the next one is the edges. There are two types of edges in rack, which are the request edge and the assignment edge. Okay, for the edges, request edges represent the waiting state of the process. It represented with an arrow pointed from a process to a resource, like this one, process P1, and this is resource. It is pointed from P1 to the resource. Okay. The next one is the assignment edges. It represents the allocation of resources to the process. Okay, for example, it also represented by an arrow pointed from a resource instance to a process. For this example, there are the dots represent the instances of the resources, and each point to a process. So it means the instance has been allocated to the process. Okay, for summaries, to summarize the rack, the symbols in rack, process represented with circle and the name of the process in the middle, resource with the number of dots depending on the number of instances, the assignment, the request edge, which is pointed from a process to a resource, and the allocation edge, which is pointed from an instance of the resource to a process. Okay. So let's see how a deadlock can be represented in a rack. So we got this graph where the resources are X and Y, and the process are A and B. As we can see here, an arrow is directed from X to A, which means A is holding X, which is the assignment group, assignment H. And for the next one, you can see that an arrow has been pointed from A to Y, which means A is requesting requesting for Y. Okay? A is holding X, also waiting for Y. Okay, the next one we can see that an arrow is pointed from Y to B, which means B is holding Y, and an arrow is pointed from B to X, which means B requests X. So as we can see here, there's a cycle here. B is waiting for X, but A is holding X, but also B is holding Y, and A is requesting for Y. So A and B is waiting for the other, will wait forever. So the deadlock happens. This is the example how the deadlock happened in rack.
For the next part, I will be showing you how to avoid a deadlock. Learning to avoid a deadlock is equally important as identifying the deadlock. Before we get into it, there is literally difference between prevention and avoidance. For example, we can prevent deadlock by letting at least one of the deadlock conditions to fail. And there is deadlock avoidance, where we can ensure a system is in a safe state. Okay, there are two methods which we can do to avoid a deadlock. They are RAG allocation schemes and safety algorithm. RAG use a variant of claim edge. Claim edge indicated that process A may request resource Y and process B may request resource Y. Hence, the RAG shows no cycle, so the system is in a safe state. Claim edge convert to request edge when a process is requesting a resource. As you can see, process B requesting resource Y, when previously process B is just claiming the resource. RAG turning from safe state into unsafe state because there is a cycle in the graph. Moreover, if the request edge convert to assignment edge for resource Y and process B, then the deadlock will occur. Therefore, the request for process B cannot be granted to avoid a deadlock. The request can be granted only if converting the request edge to assignment edge does not result in the formation of a cycle in the resource allocation graph. Otherwise, the process must wait or we must delay the request.
Today, I'm going to explain about safety algorithm from the topic deadlock. Basically, Banker's algorithm is a deadlock avoidance algorithm. It is also used for deadlock detection. This algorithm tells that if any system can go into a deadlock or not by analyzing the currently allocated resources and the resources required by in the future. The Banker's algorithm consists of the following two algorithms. One is request resource algorithm and the second one is safety algorithm. Since my part is only covered for safety algorithm, I'll explain about safety algorithm. The data structures involved in Banker's algorithm are: one is available, two is max, the third one is allocation, and the last is need. Available is a one-dimensional array that tells the number of each resource type currently available. Max is a two-dimensional array that tells the maximum number of resource type required by a process for successful execution. Allocation is a two-dimensional array that tells the number of types of each resource type that has been allocated to the process. And the last one, need, is a two-dimensional array that tells the number of remaining instances of each resource type required for execution. These are the steps doing safety algorithm. The first one is we let work and finish be vectors of length m and n respectively. Initially, work equals to available and finish array equals to false for I equals to 0, 1 until n minus 1. And the second step is we find an index I such that both finish I equals to false or need I less or equal to work. If no such I exists, go to step 4. Step 3 is we perform the following where work equals to work plus allocation and finish I is equals to true. Go to step 2. And the last step is if finish I equals to true for all I, then the system is in a safe state. Otherwise, the system is in an unsafe state. This is the example question where we need to find the need. Need can be found by max minus allocation. For example, 7 minus 0 is 7, 5 minus 1 is 4, and 3 minus 0 is 3. This is the example method on how to check whether the system is in a safe state or not. As I mentioned earlier, the first step is we set work and finish be factors of length m and n here. Then we initialize our work equals to available, where our work is 332, and our finish array equals to false. Next step, for I equals to 0, where our need is 743. To proceed to step 3, we need to fulfill two statements, which are finish I equals to false, and the second one is need I less or equal to work. But in our case, since the first statement is only fulfilled and the second statement is not, since our need 0 is bigger than the work, P0 must wait. We do this step for every I until both statement is fulfilled. Once we achieve this statement, which is like this, we perform the following, where work equals to work plus allocation, and also finish I change to true from false. If all I for finish I is equals to true, hence the system is in a safe state.
For the conclusion part, I will be summarizing what we have learned in this video. First, what is deadlock? A deadlock state occurs when two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting process. Second, when will be the deadlock occur? Deadlock occurs after the system satisfies all four conditions. Those conditions are no preemption, halt and wait, mutual exclusion, and circular wait. Third, how to handle deadlock? We can prevent and avoid a deadlock. To avoid a deadlock, there are two methods used, which they are resource allocation algorithm scheme and safety algorithm.
Throughout this project, we have used multiple online platforms such as Google Doc, WhatsApp, and Google Drive as a means to collaborate and communicate with each other. Overall, thank you for watching.